Okay, let's look at free response 1991 AB4. It says let f be given by the function f of x is equal to the absolute value of x minus 2 over x minus 2. First question says find all zeros of f. Well, how do we find zeros? Zeros are really x-intercepts. So when I'm looking for an x-intercept, I'm just looking for where the graph crosses the x-axis. So what I want to do is I want to figure out where f of x, where f of x equals 0. And if I want to do that, I want to figure out where this fraction equals 0. So when I do that, I'm going to have the absolute value of x minus 2 over x minus 2. I'm going to set that equal to 0. Well, here's the thing. The only time a fraction can equal 0 is when you have 0 divided by some number. It can only be 0 divided by number, and it can't be 0 divided by 0. You can't have 0 in the denominator. So that means you can't, one of the first things you're going to notice is that x cannot equal 2. Because if x does equal 2, you're going to get a 0 on bottom. And the only way we're going to be able to make this fraction equal 0 if just the top equals 0. So you got to get 0 divided by a number other than 0. So you can't have 0 over 0. You want 0 divided by something other than 0, like 3 or 4 or 5 or negative 5 or negative 10. So I just need to really, for part A, all I got to do is consider where the top equals 0. So I'm just going to take the top part, absolute value of x, minus 2, and set it equal to 0. Add 2 to both sides, you get absolute value of x is equal to 2. And then absolute values is piecewise, so we're going to get x equals plus or minus 2, but we've already stated that x cannot equal 2 because that gives us 0 in the denominator. So we're just going to say our only 0 is x equals negative 2. That's our only 0. That's the only place this graph is going to cross the x-axis. Now, some of you are probably asking, what happens at 2 then? Well, if you get 0 over 0, if you get 0 in both places, because 2 did give you 0 on top, but it also gave you 0 on bottom, that is what you call a hole. The graph has a hole at 2. Alright, anytime you get 0 over 0, you know that canceling takes place and you're going to get a hole. So, with that said, let's go on to part B and C. Part B and C deal with a derivative. They want you to find the derivative at 1 and at negative 1. Well, to do that, we need to go ahead and look at this piecewise function. So absolute value of x minus 2 over x minus 2. In order to do it, we don't have a rule for absolute values, a derivative rule, so I need to define it piecewise. So I'm going to define the function piecewise. Well, really the place you got to pay attention to is the absolute value. There's two things. To get rid of this absolute value, we have to think about what's in the absolute value. Where is it going to change from negative to positive? Well, at 0. So that's where we're going to splice our piecewise together, is at 0 because of what's in the absolute values. Now, positive piece would just be, if x is positive, you don't even need the absolute values. It'd just be x minus 2 over x minus 2, which is really just equal to 1. And that's for x greater than 0. Okay? And you could put an equal to on this if you wanted to. It really doesn't matter there. You got to put an equal to somewhere. It can be on the greater than or equal to or the less than. And some people are like, well, wait a minute, you said it couldn't be 0. That doesn't make the denominator 0. If I plug 0 into the denominator, I get a negative 2. So 0 is fine. It was 2 that wasn't fine. Now my negative piece is going to be when x is negative. So if x is negative, the only way to get rid of the absolute values is to do the opposite of x. It's not the opposite of the quantity, it's just opposite of x. And that'll be, let's do x less than 0. So there it is defined piecewise. I have the two pieces. Now I can find my derivative so that I can plug in 1 and negative 1. So when you do a derivative of a piecewise function, it's pretty easy. You just take the derivative of each part. So the derivative of the first part is just going to be the derivative of 1, because x minus 2 over x minus 2 canceled, which gave us the whole at 2. And it became 1. So that derivative, when you take the derivative of it, it's going to be 0. Now, people always ask me, what happens to your domain when you do this? Well, first of all, let's just write down derivative of 1 was 0, so we got that, comma. It's still going to be x greater than 0, but you're going to lose the equal to. And you always, if there's ever an equal to, as soon as you take the derivative, you lose that. So again, you're going to lose that equal to every time, and that's because piecewise, you're joining two different functions together, so it's some kind of corner or cusp, or it possibly could be a jump. So we just lose that equal to. The next piece, when you take the derivative of it, you're going to have to use quotient rule. So you're going to have to go derivative of tops, -1, times the bottom, minus the derivative of the bottom, times the top, over the bottom squared. And that'll stay x less than 0. Now let's simplify the derivative. So we're going to have f prime of x is going to be equal to the piecewise function 0 for x greater than 0. And in this next piece, you're going to get a negative x, and here's going to be a positive x, so the x's are just going to cancel. So the x's cancel. You get a positive 2 and a positive 2, so that's going to be 4 over x minus 2 squared. And that'll still be x less than 0. Now I can find part B and part C. So f prime of 1 for part B, which piece would I plug in for 1? I'd use the top piece, because that's where 1 is bigger than 0 for my domain. So 1 fits in the top piece, and no matter what you plug into the derivative, if you use the top piece, it's always going to equal 0. So f prime of 1 is 0. So there's part B. Part C, f prime of -1. I'm going to use the bottom piece. So now I'm going to plug in -1, because -1 is less than 0. -1 minus 2 is -3. -3 squared is 9, so we're going to get 4/9. So there's my derivative. Find the range of f. Okay? Well, to find the range of f, I really need to graph the original function. So to graph this, I really need to look at the graph of this thing. So if I go, I'll do a quick sketch of it right here in the middle of my page. I'm kind of running out of room. But you know a couple things. First of all, you know there's a 0 at -2. So I know it crosses at -2. Okay, so I can put that there. It crosses at -2. And then I know greater than or equal to 0, it's a horizontal line at 1. So the right half looks like this. And then the left half is a rational function. And we know it crosses at sorry about that, my kid came in. So this next part's the rational function, okay? So if you look at this rational function, hopefully you notice it has a vertical asymptote at 2, but that's over here. And since it's less than 0, the vertical asymptote's not going to do anything. So we're not even going to see that. And then we know it crosses at -2. And then you're trying to figure out, okay, well, what does it do? Well, let's check out. What's the end behavior for this thing? Well, it happens to have a horizontal asymptote. If you think about the limit as x approaches -infinity, largest power on top's -x, largest power on bottom's x, so it's going to approach -1. So I know that this left half of this graph is going to approach -1. So I know it's going to go something like this. Now, where does it go from here? Does it actually connect with that piece? Well, let's check it. Plug in 0. If you plug 0 on top, you're going to get 0 minus 2 is -2. Plug 0 on bottom, you get a -2. And -2 divided by -2 is 1. So yeah, it's going to connect right into that piece. So it does. It looks like, and I can draw this a little bit better. So it looks like this in blue. This is that piecewise graph. So the range of this graph looks like to me, the range for part D would be, it goes from 1 down to -1, but it never touches -1. So you could write the range. You could either say the set of all numbers y such that y is greater, actually we could do it this way, since it's in between those. We could say -1 is less than y, which is less than or equal to 1. Or if you like the interval notation better, you could just say the range would be from -1 parentheses, because you don't include the -1 because that's a horizontal asymptote, to 1 closed. And there's your range for this function.